Our project was the use of model predictive control on a 7 degree of freedom robotic arm to generate and follow a trajectory in joint space. The trajectory generated is based off of a target trajectory of the end effector in Cartesian space. Robotic control is an area of large amount of active research due to the increasing autonomization of the world, whether it be in warehouses, restaurants, or even in our homes. With the complexity of higher dimensional manipulators, the solution to the control problem becomes unclear, and as of today, there does not exist a single unified control standard governing high degree of robotic manipulators, which makes the integration of robotic systems quite difficult. Our custom arm provided us a unique opportunity to design and implement our own controller for motion planning, given that we had access to custom hardware. Whereas most commercial arms, such as the Baxter or Sawyer, have built-in motion planning algorithms that cannot readily be accessed or modified by the user, the robot arm we are using in our project is much more of a blank slate. We have freedom to view, modify, and add to existing control strategies and observe the results of these modifications. Furthermore, our robot uses brushless motors with small gear ratios and is designed for compliance and interaction with humans. This means that our robot will encounter many potential disturbances with its environment that are difficult to prepare for. And on the flip side, any development we perform on the arm would help further the field of cooperative robotics. In particular, for this project, we wanted to create a controller that could follow pre-computed prototypical trajectories, like moving in a circle, straight lines, or shapes with corners. Given that we can categorize large swaths of useful trajectories as combinations of these movements, like turning a key in a door, picking up an object from a table, or putting something on a shelf. Knowing that our robot can follow these prototypical trajectories robustly allows for very complex, higher-level motion planning. The major challenges of our project can be described as follows. First, robotic manipulators naturally have highly nonlinear dynamics, and the custom design of our arm meant that we would have to specially account for inertias, Coriolis forces, and gravity. This precluded the use of many common linear methods in our control design. Second, since the state and input space for the 7 DOF arm sums to 21 dimensions, the simple brute force dynamic programming method earlier from this course was not suitable, both for offline runtime and memory constraints. Even for a more suitable method, runtime would be the biggest issue. Third, our controller needed to be aware of the joint position and torque limitations of the arm, so we had to use a method compatible with both linear and nonlinear constraints. Fourth, we had to mediate the trade-off between following trajectories closely and operating quickly enough that the robot could still perform tasks at a reasonable rate. This was mostly a tuning problem, and thus we had a bit more leeway on how precise we wanted the arm motions to be.
We generated a Universal Robot Description Format file, or URDF, for our robot arm from the CAD model using a SOLIDWORKS URDF generator plugin. This generator returns kinematic geometry, inertia matrices, and estimates of mass and the center of mass. Using MATLAB's Robotic Systems toolbox in conjunction with the URDF, we were able to derive the Lagrangian dynamics of our system according to the equation shown. Here we see the general form of our model. In this equation, theta represents the joint state positions, m the inertia matrix, c the matrix of Coriolis forces, and n is a vector encoding other nonlinear forces. In our case, this is a force due to gravity. As can be seen, every term is nonlinear in the state.
Our controller was a model predictive controller that performed constrained finite time optimal control at multiple time steps using a modified version of the standard LQR controller we learned about in this class. In particular, it was modified for the purpose of trajectory following, with a similar setup to the one presented during the first midterm, with the cost function itself changing every time step. We chose this particular controller because we wanted to implement a form of optimal control while minimizing extraneous torques or movements. This is in line with the goals of cooperative robot control we outlined before. We want a fast, effective, and safe controller. We had the choice to control the position of the end effector in Cartesian space or the input torques to the 7 motors in the arm, but decided ultimately to control the input torques because we had direct access to current, and controlling for Cartesian position could potentially be a further detriment to our runtime due to the need to run more inverse kinematic calculations per time step. We tried to minimize the horizon of the constrained finite time optimal control step as much as possible, and actually found that the simulations ran with feasible solutions even when n took on values in the range between n equals 2 and n equals 4. So that is where we ran all of our simulations. For the sampling time in the discretization of our system dynamics, we usually used between 50 and 60 Hz, which mimicked the actual operating conditions of the robot. We found that simulating at higher rates than that was impractical and took too much computation, but simulating at slower rates resulted in instabilities and infeasible outputs from the solver. Like on the midterm, the position costs were zeroed around the current point in the pre-computed trajectory we wanted the end effector of the arm to follow. We allowed the arm to switch the target trajectory point after the Cartesian distance to the current point was below a certain epsilon value, so it would not have to spend time converging exactly to each individual target. We also implemented additional modifications to the cost function concerning the velocities and input torques. First, we zeroed the velocity costs around the velocity from the previous time step in order to preserve the momentum of the arm and prevent deceleration when approaching each target point in the trajectory. Similarly, we also zeroed the input torques around the torque required to statically hold the robot in its current configuration, computed with MATLAB's gravity torque function. Previously, weighting the torques in the cost function would cause the robot to droop along the trajectory because it would be reluctant to provide any energy to counteract gravity. After this change, however, we were able to weight the torques more reasonably and attempt to penalize jerky movements without letting the arm droop. For the purposes of benchmarking, we used fmin_con as our nonlinear function solver, as it is commonly available. While fmin_con is not an extremely fast nonlinear solver, we did have control over the gradients to pass in. Since we were using modified LQR for the cost, we very easily calculated the cost gradients using the multivariate chain rule and the symmetry of P, Q, and R. This caused a noticeable increase in the computational speed of the solver. Additionally, fmin_con was able to take in nonlinear constraints, so we were able to characterize our system dynamics effectively over the length of the simulation. Finally, we also wanted to explore the robustness of our controller. To do this, we modeled disturbances as forces applied to the end effector of the robot, which approximated someone pushing the robot in some direction off its trajectory. We generated the forces with some predetermined probability at each time step, and normally distributed their components with a standard deviation of about 1 Newton.
Overall, our simulation results were very promising. We chose 2 prototypical trajectories to perform our tests on, a box and a helix. We thought that these trajectories exhibited many qualities that could be used to benchmark good trajectory following, including sharp corners, long distances with twisting motions in space, and a combination of straight and curved lines. Some of the important characteristics of our controller that we wanted to verify were the speed and smoothness of its trajectory following capabilities and how that compared to the precision and accuracy of the trajectory tracking. To characterize this, we created tools to visualize the target trajectory, the trajectory of the end effector, and the overall look of the robot over the course of the robot's motion. There were a few salient factors here. We noticed that when n increased, the arm seemed to move faster overall along the trajectory, which made sense to us because each step in the MPC would be more farsighted, meaning that it knew to attempt to preserve its momentum for long periods of time and would accelerate more as a result for that time step. Without disturbances, however, n did not have too great of an effect on the accuracy of the tracking. Decreasing the cost on input torques predictably would increase the acceleration of the arm and allow it to travel along the trajectory much faster. Sometimes, this led to a little wobbliness or other loss of accuracy in tracking, which was also to be expected. In the end, we decided to maintain higher values of R because decreasing the amount of acceleration of the arm also aligned well with the safety goals of our controller design. There were some benefits to zeroing the velocity costs around the velocity from previous time step. First, our simulations in the total time spent moving along the trajectory dropped, as expected, since the arm would move towards each trajectory point much faster. Second, the speed along the trajectory was also much smoother. This eliminated a previous problem where the arm would accelerate and decelerate between points in our pre-computed trajectory instead of just trying to smoothly travel between them. One drawback of doing this, however, was that since our velocities were controlled in joint space, the momentum preservation also occurred in joint space, which did not always translate well to Cartesian space. Oftentimes, if one joint was rotating very quickly at one time step, it would cause the end effector to slightly overshoot in the following time steps. However, by increasing the cost on distance from the trajectory, we were able to constrain the overshoots reasonably. After we confirmed that we could follow our chosen trajectories closely, we added in disturbance generation. We hypothesized that using a lower constrained finite time optimal control horizon would be very detrimental for disturbance rejection, and our results were generally consistent with that hypothesis. We found that for n equals 4 compared to lower values like n equals 2, even when multiple forces were applied within a short time period, the arm was able to stabilize itself and stay on the trajectory. Furthermore, it was able to generally reach the end of the trajectory only slightly slower, because the controller weighted distance from the trajectory points more heavily than preservation of velocity. Other than this consideration, the disturbance rejection performed fairly well under a variety of conditions, and we determined that our controller met all of our high-level goals except for computational speed, which prevented us from running our controller in real time.
In addition to our simulation animations, we also plotted joint states and used these graphs to inform us more quantitatively about the effects of our tuning on the behavior of the robot. For example, in many of the simulations of lower costs on velocity or input torques, we were not able to easily quantify how poor trajectory following was just by looking at the animations. We instead turned to plots of the joint states and velocities, and were able to clearly discern how high our joint velocities were rising, or how smooth the joint states were changing. However, while these plots were useful, without the animations of the arm's motion, it was very difficult to completely characterize the performance of our controller's settings. Both tools were invaluable to the interpretation of the data from the other. Performance has been the limiting factor throughout our project, especially due to the fmincon solver. We managed to achieve a 5-time speed up by providing fmincon with analytical cost gradients, and providing analytical gradients for dynamics should improve performance further. We hope to do this by evaluating the functions in the robotics toolbox using symbolic variables and differentiating the result. This idea did not work because the robotics toolbox only supports numerical computation. We then tried re-implementing the toolbox functions using symbolic variables. Our symbolic dynamics functions are mostly working, but we did not integrate them into the project due to time constraints. Since we use a general nonlinear solver, we have the opportunity to use non-quadratic cost functions. In the future, we could explore whether changing the form of the cost function improves trajectory tracking. Additionally, we can modify the cost function to penalize being near the joint limits. This would help avoid singularities that occur when the arm is either fully extended or fully folded in on itself. Some form of soft constraint might be appropriate here. Whatever the solutions we decide to implement in the future, we hope that we can move beyond just simulating these results to eventually controlling the arm in real time.